First, a short announcement. During these Friday meetings, we will now give a few updates on what's happening in the mathematics and mathematical sciences community in the upcoming weeks. And this morning's announcement is that there is the 14th Johannesburg School on String Theory at UP from the 29th of April to the 3rd of May. So string theorists and people interested in string theory, please note that. And now to our seminar for today. And let me introduce Bruce Bartlett, our speaker, singer and ukulele player of note. He is an associate professor of mathematics at the University of Stellenbosch and works in the area of quantum topology, in which he looks at topological invariance of knots and three manifolds using invariance inspired from quantum field theory. These invariants relate diverse mathematical areas, such as representations of Lie groups, differential geometry, and category theory. But in particular, today, Bruce is going to talk about the quintic, the icosahedron, and elliptic curves. All of those areas have long histories and have deep roots in all areas of mathematics. So, Bruce, over to you.
Thanks, Bruce, and thanks for that introduction, and thanks for the opportunity to speak in the seminar. So, on the 16th of January 1913, a young Indian clerk from Madras wrote to the foremost British mathematician at the time, G.H. Hardy, at Trinity College, Cambridge. Here's his letter. Dear Sir, I beg to introduce myself to you as a clerk in the accounts department of the Port Trust office at Madras on a salary of only £20 per annum. I'm now about 23 years of age. I have had no university education, but I have undergone the ordinary school course. After leaving school, I've been employing the spare time at my disposal to work at mathematics. I have not trodden through the conventional regular course, which is followed in a university course, but I am striking out a new path for myself. I have made a special investigation of divergent series in general, and the results I get are termed by the local mathematicians as startling. I remain, dear sir, yours truly, Srinivasan Ramanujan. So here was the famous letter which Hardy received from Ramanujan. The first page was typewritten, and then the next 10 pages were handwritten notes of Ramanujan's, where he listed a whole bunch of equations that he had proved, well, that he had calculated, should I say. You can have a look here, beautifully written out. This is page 7. Page 8 was lost to history, unfortunately. This is page 9. Page 10 was lost to history. This is page 11, and that's the last page. Let's go back to page 9, because this is the one I want to focus on today's talk. Specifically, this bunch of equations here, 4, 5, and 6, and 7. And let's focus in on this guy here. What's going on here? So it's this intriguing expression for this continued fraction on the left-hand side. And Hardy famously said that this particular formula and its cousins defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, No one would have the imagination to invent them. I'm going to explain how Ramanujan's beautiful formulas can be understood using the geometry of the icosahedron. Right? Icosahedron is the fifth and most mysterious Platonic solid. In fact, I will spell out a remarkable dictionary that translates between the following mathematical worlds. Firstly, we have the icosahedron. So you want to be thinking of this shape. The other world is the world of quintic polynomials. So something like this. And the third world is the world of elliptic curves and modular forms. So things like this. Along the way, we'll meet our old friends Kepler, Gauss, Abel, Galois, Klein, and of course, Ramanujan himself. So strap in for the ride. Let's start with Arnold's proof of the unsolvability of the quintic. So we're all familiar with the roots of a quadratic equation, x squared plus bx plus c equals naught, when you can solve for the two roots in this way. We learned that in high school. For a cubic equation, x cubed plus bx plus c equals naught, we had Italian mathematician Cardano's formula from 1545. A little bit more complicated. There's also a formula for the roots of a quartic equation, so to the power 4 due to Ferrari, also in 1545. These guys competed with each other. This one is a lot longer, so I won't write it down. But Ruffini in 1799 and Abel in 1824 showed that there's no such radical formula. A radical formula means one built out of the standard operations of plus, minus, times, divide, and extraction of nth roots for the roots of a general quintic. So, rather a remarkable fact. Arnold, who's a Russian mathematician, gave a wonderful topological proof of this in 1962, different to the traditional proof given by Abel and Ruffini and Galois, as is normally taught at university. So consider the dance of the roots as the parameter b moves in the complex numbers for the following quintic equations. Okay, so I'm trying to solve for the roots of this equation. Here, b is a complex number which I can vary. So for each different value of b, I get a different equation. This kind of quintic here is called the Brioche quintic. And essentially, every quintic can be reduced to this form by a change of variables. Okay, so here we've got the b plane. Here's my point b. So here maybe b is equal to 1. So I'm solving a particular equation, x to the 5 plus 10x cubed plus 45x plus 1 equals 0. I can extract out the roots, say on my computer, and I'll find there's going to be 5 roots, x1, x2, x3, x4, x5. Now I'm going to move b around in the b plane. And as I move b around, the quintic equation changes, so the roots start moving. These 2 points here are where some of the roots coincide. So for these 2 particular values of b, some of the roots will coincide. That's why I've marked them as special points in the b plane. So I've now done a loop in b space. And look what's happened to the roots. The roots have been permuted. They've done a dance and they're permuted. And if we were to trace out what's happened, x1 went to x4, and x2 went to x1, x3 went to x5, x4 went to x3, x5 went to x2. That's called the monodromy of the roots around this loop in B space. If I were to do a different loop in B space, say this loop here, where I have to loop around this point, then the roots will dance around differently. You see now these 3 roots permuted cyclically amongst each other, and these 2 roots went back to where they started. So it's a different permutation that's occurred. And the point is that these two permutations generate all possible even permutations. So you can get any possible even permutation of the roots by doing some loop in the B plane. The problem is that the monodromy you can get from a radical formula can't be very complex. It has to be a solvable group of permutations. You can't get an arbitrary group of permutations from a radical formula. And this A5 is simple, meaning it has no normal subgroups. To be a solvable group means you have to have a chain of subgroups whose quotients are abelian, but in particular, a chain of normal subgroups. So if you are simple, you can't possibly be normal. And in the next slide, I'll show you a nice proof to see that A5 is simple. So therefore, it's not solvable. So therefore, you can't write down a radical formula for the roots of a general quintic. Very nice topological proof looking at the dance of the roots. So into the icosahedron. There it is. It has 12 vertices. I'm going to have to write them down explicitly in R3. So here they are. I've written them down explicitly. It's got 20 faces and 30 edges. The most enigmatic of the Platonic solids. Greeks thought that it corresponded to spirit. Let G be the group of rotational symmetries of the icosahedron. So rotations would send the icosahedron back to itself. So for example, around each vertex, we've got a 2 pi over 5 rotation through the axis passing through that vertex. Through every edge midpoint, we've got a 180-degree rotation through the axis passing through that edge midpoint. And through every space midpoint, we've got a 2 pi over 3 rotation, which rotates the icosahedron around the axis through that face midpoint. In fact, this group of symmetries is isomorphic to the group of even permutations of 5 things. How does this work? How does the rotational group of symmetries of the icosahedron end up being isomorphic to the group of even permutations of 5 objects? The things that are being evenly permuted when we rotate the icosahedron are the 5 inscribed octahedra with vertices on the edge midpoints of the icosahedron. So there's my icosahedron. I pick a collection of edge midpoints. So for example, here's an edge midpoint here, and its opposite midpoint there. There's another pair and another pair. Can't just pick any random pair. I connect them up with lines. That's going to give me an octahedron. There's exactly 5 ways you could do that. So there are 5 inscribed octahedra in an icosahedron. Let me remove the hidden lines. Maybe you can see the octahedron a bit clearer. When you rotate the icosahedron, these octahedra are going to be permuted amongst themselves. That's how this isomorphism works. Now, the group of rotations of the icosahedron is clearly simple. It has no normal subgroups. The reason is that to be a normal subgroup means you must be closed under conjugation. If you contain one of these rotations, say about a vertex, then you must contain all, and you're a normal subgroup, then you must contain all rotations about vertices. On the other hand, if you contain all rotations about vertices, then you must contain rotations around edge midpoints and face midpoints, because they can be expressed as a product of rotations around certain vertices. So in other words, if you're a normal subgroup, then you're the whole group. So that means, let's give that A5 is simple, because they're isomorphic to G. So that's a nice simple way to check that A5 is simple. And as a consequence, we've got our first connection between the quintic and the icosahedron. This, as I explained on the previous slide, this explains why there's no radical formula for the roots of a general quintic. Of course, I could have done that proof differently, but nice to see. So this idea of inscribed Platonic solids goes back to Kepler, who came up with a model for the solar system based on this idea. The planetary orbits were sort of the inscribed platonic solids. So in fact, we will establish a G equivariant bijection between the following two sets. The first set is a set of evenly ordered roots of a quintic equation, Brioche quintic, and the set of points on the icosahedron. So given a point on the icosahedron, I can give you a collection of roots evenly ordered for some Brioche quintic. That's the fundamental relationship between the quintic and the icosahedron. So I should say that this talk is based on an article that I had published in the notices of the AMS. So it's a lot of the stuff was definitely known. This work goes back to Felix Klein and others, but the precise bijection that I'm pointing out here is not very well known, and aspects of the story are not known at all, which I'm writing down for the first time. So in a sense, I'm taking the story, tidying it all up, and bringing to the fore certain pieces of mathematical structure which people hadn't written down before. So tidying up the whole story. And so if you get nothing out from this talk, just remember this one thing. Points on the icosahedron correspond to roots of a Brioche quintic. Okay, so to understand this, I need to talk about G-invariant polynomials. So inflate the icosahedron so that its edges live on the two-sphere. Call that the round icosahedron. We'd like to understand the quotient space S2 quotiented out by this G action. To do that, we're going to need to find G-invariant functions on S2. Now, the group of rotations of the icosahedron is a subgroup of all rotations of 3 space, SO3. And we have the double cover of SO3 being SU2, 2 by 2 unitary matrices, determinant 1. So define G hat to be the binary icosahedral group, which is the double cover of the icosahedral group, but now living inside SU2. So G had 60 elements, whereas its double cover has 120 elements. Sometimes need to translate between the two. Okay, the other translation we're going to need to do is we've got the two-sphere identifier with one-dimensional complex projective space, which is by definition the set of all one-dimensional linear subspaces of C2. And the way that identification works is you just do stereographic projection from the North Pole. So I've got a point in S2. I can stereographically project it to get out a point on the complex plane. And that point on the complex plane, I can think of as living inside complex projective space. I can add the point at infinity that would account for the North Pole as well. Once I've gotten here, and I can get into projective space by just saying if it's a complex number, I just send it to this linear subspace of C2. And if it's infinity, I send it to this linear subspace of C2. Okay. This is a standard identification, but I'm just making it clear that I need to do that. So here's my round icosahedron. If I stereographically project it onto the complex plane, it's going to look like this. And I'm going to sort of work interchangeably with these 2 points of view. So under the identification of S2 with CP1, the SO3 action on S2 lifts to the natural SU2 action on CP1, right? Because CP1 is one-dimensional subspaces of S2 of C2, so that means 2 by 2 matrices is going to act naturally here. So now, what we really want is G. If we want G invariant polynomials on R3, it'd be better to seek G hat invariant homogeneous polynomials on C2. So let's try and write such things down. So we've got the vertex polynomial B of degree 12, which vanishes on the one-dimensional subspaces of C2 corresponding to the icosahedron vertices. So I take to each vertex of the icosahedron, there's a certain linear form, which I can write down, which vanishes on that vertex. And that linear form is the guy which vanishes on that vertex. Okay, so just to make this clear. Example, here's a vertex here, the south pole of the icosahedron. It corresponds to this point in projector space. Such a point in projector space is a complex line in C2. So I'm looking for a function on C2 which vanishes on this complex line, and it would exactly be this function here. So that would be my first factor, U. Now let's go get another vertex of the icosahedron. Here's the north pole. It corresponds to this point in CP1. So that's a certain line in C2. So a linear function which vanishes on that line would be this function. So that's my second factor of the vertex polynomial. Get another one. Here's another vertex of the icosahedron. When I stereographically project it, it corresponds to this point. When I think of it as a complex line in C2, then the linear form which is going to vanish on that complex line would be this form here. So that's my next factor, and so on. So I get 12 factors, each of them are the linear forms vanishing on the vertices. Now multiply them all out, and you'll get this expression once you simplify it. Okay. I know this is G hat invariant. Why? Because when I rotate the icosahedron, vertices get mapped to other vertices. So all that's going to happen is that these factors are going to be permuted amongst themselves, and I'll multiply them all out. I'll get out an invariant quantity. So that's the vertex polynomial. The homogeneous polynomial of degree 12, a G hat invariant polynomial on C2. Okay. And similarly, we have the face polynomial of degree 20 vanishing on the face midpoints, and the edge polynomial of degree 30 vanishing on the edge midpoints. Go through the whole procedure, multiply them all out, and you'll get these expressions here once you simplify. And finally, we also have the vertex polynomial of the inscribed octahedron. There's 5 inscribed octahedra. Each of them have their own vertices, right? There's 6 vertices in an icosahedron, sorry, in an octahedron. And so we have a vertex polynomial for each octahedron, which is going to be of degree 6. So I've written down the vertex polynomial for the first octahedron, and then there's similar ones for the other 4 octahedra. They are of degree 6 in U and B. Calculate these things explicitly. Good. So now I can explain the precise connection between the icosahedron and the quintic. I did say it before, but now I'm showing how I got there. To define the octahedral functions to be the octahedral polynomials multiplied by minus v squared over e. Remember, this is of degree 6 in U and B. B is of degree 12, so b squared is of degree 24. So 24 plus 6, the numerator is of degree 30. The edge polynomial is of degree 30. So this thing on the right-hand side is of degree 0 in U and B. A homogeneous polynomial of degree 0 in U and B, well, sorry, not a homogeneous, but a rational function of degree 0 is going to correspond to a function on S2, right? So it's just a normal function on S2. If you sub in an edge midpoint here, then you're going to get infinity. Okay. Otherwise, it's well defined everywhere. In other words, to every point on the round icosahedron, we can associate an ordered list of 5 complex numbers. So here's a point Z on the round icosahedron. We can then calculate the 5 octahedral functions applied to Z, and I'm going to get 5 numbers in the complex plane by calculating these numbers here. And voila, I've constructed a quintic. When we rotate the icosahedron, the 5 inscribed octahedra undergo an even permutation, as I explained earlier. So, for example, if I were to rotate the octahedron around this vertex by 2π/5, this octahedron will get rotated into this one. All right. So that means that the 5 complex numbers are going to get permuted because the 5 octahedral functions are going to get permuted, right? Each of these functions are going to get permuted because the octahedra themselves are getting permuted. But the polynomial, which is formed by taking x minus those numbers, taking the product of x minus x1, x minus x2, and so on, that's going to be invariant because only thing that's going to happen is that when I rotate the icosahedron, these factors are going to permute. If I multiply out all the factors, I get an invariant quantity. So the polynomial is G-hat invariant. If you've got an invariant polynomial, that means that each of its coefficients are G-hat invariant. So let's multiply out this polynomial. I know what these things are. This is the octahedral functions, which is formed from the v squared and the e and so on. So I sub it all in. I multiply this whole thing out. A lot of algebra here. And when you do, you get a remarkably simple expression of this form. You get out a quintic, obviously, in x, and the coefficients have this pattern where that parameter b is minus v to the 5 over e squared. Isn't that beautiful? So I multiply out the polynomial constructed from the octahedral functions, and I'll get out a brioche quintic with a certain parameter b. That's the fundamental relationship between the icosahedron and the quintic. So yeah, I plotted that function b, by the way, on S2. You can see the absolute value maps to the brightness, while the argument maps to the hue. Note that the zeros of b occur at the vertices of the icosahedron. Why? Because here's this function. It will be 0 at the vertices. Right? There's the 12 vertices where it's 0. And it's going to go to infinity at the edge midpoints because I'm dividing by e. So at the edge midpoints, you can see it's going to infinity. That has a pole there. Very proud of that picture that I drew in Mathematica. I think it looks very nice. Looks like a beach ball, doesn't it? So here's a nice structural way to state what I've just said. We can state the whole thing as an isomorphism of branch covering spaces. So we formally the map which sends Z to the evaluation of the 5 octahedral functions, considered as an ordered 5 tuple of complex numbers, is an A5 equivariant bijection between points on the round icosahedron minus the edge midpoints and evenly ordered roots of brioche quintics with brioche parameter given by minus v5 over e squared. So we've got this isomorphism of branch covering spaces. One covering space is associated to each brioche quintic. I have the set of 5 roots, all evenly ordered. And the other covering space is, well, I've got the round icosahedron projecting down to the quotient space of S2 divided by G. Okay, so that's a structural way to understand the relationship between the quintic and the icosahedron. So let's boil that down into more basic language. So in other words, what's it saying? So suppose we want to find the roots of some brioche quintic. So I've got some equation like this. I'm trying to solve for x. B is some number. So I've got a specific quintic equation. I'm trying to solve for x here. The theorem tells us that what we need to do is find the point z on the round icosahedron such that b is equal to b of z, right? I've got my quintic. That means it's got some parameter b. What I'd like to do is find the z upstairs, which maps down to that b under the brioche map. If I can find that z, then I can apply the 5 octahedral functions to z, and I'm going to get these 5 points. And those would be the roots of my polynomial. Beautiful picture. So the only problem is that to go from b to z, I'm going to have to solve this equation here for z. Now, these guys here are order 60, so this is an equation of degree 60 in Z. So I'm trying to solve a quintic, which is of degree 5, and now I have to solve an equation of degree 60. That's not very helpful. But I'll show you in a second that it is actually very helpful. Anyhow, let me pause for a quick. Any questions at this point? I'm rushing through here, but such is life.
I don't think there are questions.
Okay, thanks. Good. Anyway, I'll take a sip of tea. This is an important picture.
Equation of degree 60.
Yes, because I have to solve this equation for Z.
I'm
This is-
trying to see how, why is it easier?
Okay. Cool. Okay. Okay. So one thing we need to bear in mind here is that we've got these three polynomials that I've introduced: the vertex polynomial, the face polynomial, and the edge polynomial on the icosahedron. The edge polynomials of degree 30 because there's 30 edges. Face polynomials of degree 20 because there's 20 faces. And the vertex polynomials of degree 12 because there's 12 vertices. We've got three polynomials in two variables, sorry, three homogeneous polynomials in two variables. They have to satisfy a relation, right?
Plus f minus e is 2.
Say again?
Now I'm just thinking about what's it result from graph theory about v plus f minus e is 2.
Yeah, it's like you've got you know, basically you've got three functions on C2, essentially. And so at some point they have to satisfy a relation. And indeed, you can check this one. So the first opportunity for them to satisfy a relation would be in degree 60, and you can actually check. If you calculate e squared plus f cubed, you get 1728 b to the 5. Now, if you see an equation like this, what does this remind you of? Where have you seen the number 1728? Where have you seen an equation like this before? This reminds us of modular forms, because the Eisenstein series satisfy precisely such a similar relation. E6 squared minus E4 cubed is 1728 delta. So this makes us think, maybe there's a connection between the icosahedron and elliptic curves in modular forms. Okay, so let's enter the world of elliptic curves now. So expressing a number in terms of radicals means having access to the roots of unity. In other words, the n torsion points in the abelian group C star, the non-zero complex numbers thought of as a multiplicative abelian group. The n torsion point there would be a root of unity on the unit circle. In the 19th century, mathematicians discovered that the set of points on an elliptic curve, points satisfying this equation, also forms an abelian group. It was natural to speculate that while the roots of a quintic couldn't be expressed in terms of the n torsion points in C star, perhaps they could be expressed in terms of the 5 torsion points of some elliptic curve E associated with the quintic. Okay, does that make sense? We go looking for our solutions in some more complicated abelian group instead of C star. We allow ourselves to use torsion points here. Using torsion points here basically means you got a radical formula. Using torsion points here gives you more power. Maybe that's going to allow us to express the roots of a quintic. So this is indeed the case. How exactly does this work? The way that it's described in Klein's book is very messy. I'm going to show you a much more clean way of describing this. So modular spaces of elliptic curves. So now I'm going to ramp up the math sophistication a little bit because I need to speak about elliptic curves and all that. So just to remind you, we've got a bunch of covering spaces in the game here. First of all, we've got the map from the two-sphere, or the round icosahedron, down into complex numbers, which just extracts out this Brioche map. And that's a G invariant map. In other words, it assigns the same value to each point on the icosahedron, which is related by some rotation. So all these black points, and there's 60 of them, they're the orbits through Z of the rotation group. And all of those will map onto the same Brioche parameter B. Good. And I'll just replace the complex plane with S2 because I need a point at infinity as well. So I want you to think in terms of this picture. We've got a covering space of the S2. On the other hand, here's another covering space of S2, which also has a group acting on it. It's the modular curve X5 mapping down to the modular curve X1. Okay, what are these things? X1 is the modular space of elliptic curves. And you can write that as the extended upper half plane quotiented out by SL2Z. Extended upper half plane is just the upper half plane union the rationals union infinity. Okay, so if you guys know anything about elliptic curves, you know this is like lecture 1 in a course on elliptic curves. X of 5, normally early on you learn about this. That's the modular space of elliptic curves equipped with a primitive basis for their 5 torsion. So that's the abstract way of writing it down. I could write it down in a calculational way as the quotient of the extended upper half plane divided by a smaller group of symmetries, gamma 5. Where gamma 5 is the principal congruence subgroup of level 5, means all matrices in SL2Z satisfying this congruence condition, that the numbers are congruent to these numbers mod 5.
What's the dimension
So
of SL? Sorry?
Say again?
The question on the groups. SL2Z, what's the dimension?
SL2Z is a discrete group because it's SL2Z. If you talk about SL2R, then it would be a 3-dimensional Lie group, but SL2Z is just a discrete group.
Okay. I was just thinking of the SL2R being.
Yeah, SL2R is a 3-dimensional Lie group, but we're talking about SL2Z here because we have to talk about lattices in the plane. So we have this exact sequence where you've got the projection map, the projection mod 5, going to get you down to SL2 with coefficients in the finite field of 5 elements. And then we've got the inclusion of this principal congruence subgroup into SL2Z. Right? So this here is a Riemann surface. This here is a Riemann surface. This Riemann surface is actually of genus 0, and so is this. So this is S2, and this is a copy of S2 as well, just like on the right-hand side. The group acting here is PSL2, coefficients in Z mod 5Z. Right? So if I take the quotient of X of 5 by this group, then I get X1. Just like when I take the quotient here by G, I get S2 again. And it turns out that these two equivariant covering spaces are isomorphic. They have to be. Okay, so I want to write this down explicitly. So there's actually a natural way in which PSL2 Z mod 5Z. So how does this work? I mean, how does the group of 2 by 2 matrices with coefficients in a finite field, how is it isomorphic to the group of rotations of icosahedron? Right? We have to understand that in order to get a projection between these two mathematical structures. This has got 60 elements, and so does this, and they're actually isomorphic. Can I write down a natural way in which they're isomorphic? So that's the point of this lemma, is that there's a natural way in which PSL2 comma Z mod 5Z evenly permutes the 5 inscribed octahedra in an icosahedron. I'm not going to explain that, but it's a very beautiful construction. So that gives us an explicit isomorphism of groups between PSL2Z, 5Z, and the group of even permutations of 5 things, namely those inscribed octahedra. And of course, group of permutation of 5 things we're already seeing is isomorphic to the rotation group of the icosahedron. So that gives us our map from here to here. Let's write down how this thing works, how this map works explicitly at the level of generators. So in PSL2Z, 5Z, you've got this generator. You can think of it as a Mobius transformation, then it would be this Mobius transformation. So the corresponding rotation of the icosahedron turns out to be the rotation around the z-axis, the vertex, around the axis going through the vertices of the north and south pole. So the T Mobius transformation goes over to rotation around the z-axis. Similarly, the other generator here is the S matrix. Looks like this. As a Mobius transformation, its tau goes to -1/tau. So as the corresponding rotation turns out to be, you calculate it, turns out to be a 180-degree rotation around this particular edge midpoint called alpha, edge midpoint right here near the bottom, between the South Pole and this vertex. Okay, so now Ramanujan's going to enter the story. To recall the continued fraction that Ramanujan introduced on page 9 of his letter to Hardy. Yeah, was his letter, so he has an extract from that letter. I'm talking about this continued fraction here. Okay. This thing here, basically. So how can I understand this function abstractly? So it's a very nice theorem of Duke a few years ago that you can understand this function abstractly as follows. We call it the Rogers-Ramanujan fraction because it was actually already written down by mathematician Rogers a few years before Ramanujan, although he didn't calculate some of the identities that Ramanujan did. Anyhow, so this Rogers-Ramanujan continued fraction can be understood structurally as being an equivariant isomorphism between these two covering spaces that I wrote down in the previous line. The modular space of elliptic curves with primitive basis for their 5 torsion and the modular space of points on the icosahedron. Just to be clear here, when I'm making the statement, I'm thinking of Q as being e to the 2 pi I tau. That's how I can say that R is a map from here to here. Right? That's subbing tau in the upper half plane, Q equals e to the 2 pi I tau, subbing this formula. Okay. So let's use this fact that we've got this equivariant map to calculate, for example, the formula that Ramanujan wrote down, right? In Formula 5, he told us that this remarkable continued fraction here is equal to this number. And this is the formula that impressed Hardy so much. I'm going to show you how this follows naturally from understanding that R is an equivariant map. Okay. So let's have a look here. On the left-hand side, we've got PSL2 Z, Z mod 5Z acting on the upper half plane. Now, the fixed points, and since we've got an equivariant isomorphism between the left-hand side and the right-hand side, anything that's a fixed point of some transformation on the left-hand side would have to be correspond to a fixed point of the corresponding transformation on the right-hand side. Now, if you look at the number I in the upper half plane, it's a fixed point of the transformation S, right? Remember, S sends tau to -1/tau. So I is a fixed point of that because I equals -1/I. So that has got to then correspond to the fixed point of the rotation that corresponds to S. Now remember, the rotation that corresponds to S is the 180-degree rotation around this edge midpoint alpha. So in other words, I has to correspond to alpha. Just has to, just from the fact that it's an equivariant bijection. Must preserve fixed points. I go ahead and calculate the coordinates of alpha. That's easy calculation. Stereographically project them, and I'll get this number here. So we've proved this formula as a consequence of there being an equivariant map between these two covering spaces. Very, very elegant. Okay, and the similar idea would then allow you to calculate special values of all sorts of points of the Ramanujan fraction. Duke explains that nicely. Okay. So let's summarize here. There's much more to say, but I'm running out of time. So let's summarize the algorithm for solving a quintic using icosahedron and elliptic curves. So start with a general quintic and reduce it to a Brioche quintic. You're going to end up with some parameter b. Right? So you reduce your quintic to some quintic of this form, and you'll have some parameter b, to which your quintic is reduced to that particular Brioche quintic. It's going to be an element of the set of all Brioche quintics. Remember that there's a covering space living over the set, namely the space of evenly ordered roots of each Brioche quintic. A5 equivariant covering space. So what we'd like to do is, given this quintic, we'd like to find its roots. What do we want to do, right? But that's hard. We don't know how to do that yet. Good news is that this covering space was isomorphic, as we saw, to the covering space of the icosahedron, mapping down to the quotient space. Right? So that polynomial b, that Brioche quintic, is going to correspond to this point in S2, b. So now what I'd like to do is I'd like to lift it up here. If I could lift it up here, then I'd be done. Lifting it up here means solving that equation of order 60. Okay, by the way, what the top map here is just the octahedral functions, right? That's going to give you x1, x2, x3, x4, x5. And this projection map here is this Brioche parameter. It takes a point z and then calculates the quotient of the fifth power of the vertex polynomial over the second power of the edge polynomial. If you want to invert it, it's hard. Now I can answer the question, how are you going to do this? So now I'm going to relate it to elliptic curves. So I know that this covering space is isomorphic to this covering space as well. So what you do is you need to determine the step 2 of the algorithm. You need to determine the associated elliptic curve. So that point B is going to correspond to a certain elliptic curve. Essentially, the elliptic curve whose J invariant is B. So I could easily, basically, B's. That can give me an upstairs here, by the way. I've got the Rogers-Ramanujan continued fraction being the map upstairs. Okay, so what you do, this B is going to correspond to a certain, you're going to get a, well, what do you have to do? This B is the J invariant of an elliptic curve. I then need to calculate the point tau in the elliptic curve such that C modulo the lattice span by Z1 and tau is going to give me this, have this J invariance. That essentially means calculating the periods of this particular elliptic curve with this J invariance. How do you calculate periods of an elliptic curve? Well, there's a very nice algorithm due to Gauss originally called the arithmetic geometric mean. Although that was normally just done in certain cases, so I have to do it in a more general case now. That was only done recently by Cremona in 2010 and his PhD student. Anyway, the point is you can very quickly calculate the parameter tau from B using the complex version of the arithmetic geometric mean. So this is an efficient process. Now the cool thing is that this covering space is very easy to lift, because all I do is I take that point tau and I just consider it as an element in this space. So I literally just send tau to tau. I'm just, in this space, I'm quotienting out by less than here, right? So it's sort of very easy to lift. I choose any of those lifts. It's going to be 60 of them. So that was the cool thing, is that it's very easy to lift up here. So now I've got upstairs. So that's good. Now I apply the Rogers-Ramanujan continued fraction to tau. That's going to give me a certain point Z here. The Rogers-Ramanujan continued fraction converges extremely quickly. So that's also numerically efficient. Now I've got my point Z, which was the hard thing, right? Remember, I had to solve the equation of degree 60, and we've seen how to do it. You go here, calculating the periods of the elliptic curve, lift, and then go across. And then once I've got my point Z, I calculate the 5 octahedral functions applied to Z. That's going to give me my 5 points in the complex plane. And those will be the roots of my Ricci quintic I started with. Isn't that a beautiful procedure? There's a lot more to say here and how everything fits in structurally. So the reference here is the article that I just got published in the Notices of the AMS, and then this paper of Duke that I spoke about, this thesis of Bessel's, the original book of Klein, and also see references in this article. Obviously, there's a whole bunch of other references as well. I'll stop there.
Thank you very much for a very, very interesting lecture that's taken us through hundreds of years of mathematics and many great names from the past. Are there questions, firstly, from the audience? Yeah?
Bruce,
So no need for the whole radical business. Because it's known that quintics cannot be solved by radicals.
They can't be solved by radicals, but you can solve them using elliptic curves.
So if you go to topology, you can fix the problem.
You need a bit of number theory too. Yeah.
There was a question from the online audience.
it's me, Bruce. Thanks a lot for the talk. I've seen some parts of it, and then still very interesting. But the part I haven't seen was the Roger Ramanujan identity. So of course the Roger Ramanujan identity was an identity of Q series. So this is just an application. But there was the one I'm thinking about was the Ramanujan identity has it has another application. It gives you this identities between certain number of partitions that I don't remember. So now I'm thinking, do those partitions mean anything in those geometrical objects that you have? Because the partitions are the coefficients.
Yeah. That's right. That's a great question. Yeah, when you expand this thing out, you're right. Then the coefficients have a combinatorial interpretation in terms of partitions. I haven't seen a way to link that with the icosahedron, but it must be, right? It's a good question, but I couldn't see how to link the combinatorial interpretation with the icosahedron directly.
Okay, thanks, Bruce.
But I agree with you. Well, now that you've solved the quintic, how about going up in some powers? Do you have any ideas? Do any of these ideas extend to higher order polynomials?
Yeah, so the issue is that we run out of geometry because we've run out of platonic solids.
Okay.
Yeah. So on the other hand, it is true that the roots of a sextic equation, like a 6th degree equation, can be written down using modular forms, and possibly some higher order ones as well. But you don't have a link with the Platonic solid anymore, so a lot of the beauty goes away.
Yeah, and some of your fast mechanisms of solving them with it.
Yeah. So of course, if you really want to ask a computer to solve this equation, there is a numerical method that solves for the roots of a polynomial, and it's of order like n to the between n squared and n cubed or something like this. So it's very fast, and I haven't checked the order that I
What
get
was
from
n,
this.
Bruce? Sorry, Bruce. What was the parameter n in?
I think it's a measure of the size of the coefficients of your polynomial.
Ah, okay.
This method, I don't think would beat the method that your Mathematica would use on any given quintic, but it is less than exponential. It's I think cubic or something. So it's a little bit worse than the fastest method, but I suspect it might be better than if you were to average it over all possible quintics. It might be better than the other guy, which loses out maybe on some bad quintics.
But it's lost the beauty of what's tying all of this together.
Yeah. You can't have everything, but I agree. I'm with you.
Because this is quite an amazing bringing together of different aspects of geometry and topology and things like that.
Yeah.
Are there further questions?
Just one comment. Can you hear me?
Hi, Ken. Yes, hi, Ken.
Yes. Theta functions, of course, can be used to solve algebraic equations of any order. So you could theoretically translate this into theta functions. It would probably be terribly inefficient, but it would generalize.
Thanks, Ken. That's a very good point. And indeed, if you go to the proof of why the Rogers-Ramanujan fraction is equivariant, right? This theorem here, you would express R in terms of theta functions, and then you can check this. So like theta functions are a very important ingredient.
Very interesting. Thank you. Are there further questions and comments from the audience? Well, then thank you, Bruce, for an absolutely fascinating tour of both history and topology, number theory, elliptic curves. And yes, it was extremely interesting. And thank you very much.
Thanks a lot, Bruce. Okay.